I'll just take you through the flat Earth model before we start talking about the complexities of defining datums based on the curved surface of the Earth. So when it comes to surveying work that majority of surveyors undertake every day, I would say about 99% of surveys are local surveys, not geodetic surveys. And because of that, it means that when it comes to working on smaller areas, we don't need to take the curvature of the Earth into account when we're doing our observations. So unlike the geodetic surveys. And local surveys generally are defined as surveys of smaller areas of under 10 kilometers. And so when that means when observing between points, we're sticking to that small distance of relatively small distance of under 10 kilometers. So that's why it's important to have something that we can compare our curved surface or a curved datum to when we're comparing the local and the geodetic datum. So again, we use a flat Earth model when we're working on a small surface. And I'll just change the color of this pen. Okay, so let's assume that you're working on terrain. You're working across 2 points here, A and B. And assuming that, obviously this is a plane, so it's not a two-dimensional surface, because once we project those observations onto a coordinate system, then I'll quickly explain to you what that would look like. So as the flat Earth model, which is our local data, still a 3D model. Actually, again, represent this better. I think I can do better than that. Right, so we've got two observations on the surface of the Earth, so point A and point B. And what we would normally do when we want to project these observations onto a plan or a map is that we create a grid surface that we can then project these observations on. And that projected surface is a rectangular coordinate grid. Oops. And it all makes sense in a minute. And what we have is normally 3 axes. So because it's 3D, we've got a northing, we've got an easting, easting, and then we've got heights. Okay. So you're taking an observation on a local datum, small scale survey, so let's assume under 10 kilometers. If we project these observations onto a flat surface, generally what we end up with is grid lines. Okay, so that go grid lines that we can then project our observations on. So let's assume that this will be A hyphen B hyphen. So they're just projected onto that surface. And then when we've got the eastings and northings displayed for these two observations, we can use basic mathematics to then allow us to measure distances between points as well as areas. Okay, so the relative positions of these points is what we're actually interested in surveying, because that allows us to then position and map out the areas and information that we need to derive from these observations. Now, the height of each of these points, if we're projecting that onto that flat rectangular grid, that would be our height relative to sea level. Okay, so the height is given by the vertical distance above or below that horizontal plane. So this rectangular plane is a horizontal plane, and anything projected as a height from these observations would be our height above mean sea level. Excellent. So the orientation of the axis, so we know that we can have a northing and easting, that will be our horizontal axis, and then our vertical axis is our height. Again, the thing to note is that it's a rectangular coordinate grid at sea level, and the benefit of using this local simple datum is that it's quite intuitive to use. It's nothing complex, so we can really understand even the relationships of the heights above mean sea level just based on our observations in the real world. But now when we're looking at working on the actual surface of the Earth is not obviously flat. We've got the topography of the Earth, which is quite varied. It's not a smooth surface. We call that the surface of the solid Earth. And it includes things like the land surface, the topography, as well as the seabeds. And then from there, we also have two other types of datum that we use. And one of them is the geoid, and the other is the spheroid. And I'll go through each of these individually in the next few slides. But the geoid is mainly defined as the shape of the Earth is if we were to extend mean sea level around the Earth. So that's a very simple definition. And then our spheroid is a very smooth representation of the Earth that allows us to interpret mathematical relationships between observations quite easily. So before I go ahead, just to note that spheroid is also known as the ellipsoid. So you might see the term interchanged. If it's a spheroid or if it's an ellipsoid, it's generally the same thing. Okay, so both are correct terms to use. And then we've got this term here, the oblate spheroid or the oblate ellipsoid. And what it refers to is that the fact that the Earth is not actually a sphere. So if somebody's asking you to define the shape of the Earth, it's not correct to say that the shape of the Earth is a sphere. It is a sphere, but it's squished from the north to south direction slightly, meaning that the distance along the equator is actually longer than the distance from the north to the south pole. And because of that, that squishing in the north to south direction gives it the name of an oblate spheroid. So, a rugby ball might be one of the ways to visualize this. It's obviously not as drastic as a rugby ball, but that flattening from the top to the bottom looks a bit more like a shape that is squished from the north to south direction.